Okay, today it's our last online lesson, I think. Hopefully I'll see you on Monday. So today I want to just talk about how to charge objects. So just summarizing the whole chapter on electrostatics. It's about charges on objects, and so there are two types of charges. We've got positive charges and negative charges. So this is just a little bit of basics. It's positive and negative charges. The positive charges comes from the protons, and the negative charges comes from the electrons. And we all know that there are forces between charges. So between like charges you'll have forces of repulsion. And these forces are electrostatic forces. And the charges does not have to touch for them to experience these forces. So they are called field forces or non-contact forces. And unlike charges, are forces of electrostatic forces of attraction. All right, then in today's lesson I want to talk about conductors and insulators a bit more, and I want to talk about the distribution of the charge on conductors and insulators. And I think in our previous lessons we discussed the principle of conservation of charge. So there are three ways in which charge is distributed to objects. The one is through friction, the other one is through contact, and the third one is through induction. And I want to talk about those things in this lesson. Conservation of charge and all the calculations that we must be able to do, we've discussed that in the previous lessons. This thing is a bit slow to react. So first of all, I want us to draw some sketches where we show the forces between charges. So we look at objects that are identical, and we're going to look at the forces between opposite charges. Are you still there, Talita?
Yes, ma'am.
Okay, good. The opposite charges, the one object will be positively charged and the other object will be negatively charged, and we name them object A and object B. And my diagram is a bit crooked, but those objects are the same size. So what type of force will we have between these two charges?
Pardon me?
What type of force will we have between the two charges? They are electrostatic. Oh, somebody I think is trying to come in. Is that so? I can't see anything. Electrostatic forces, and between opposite charges, the electrostatic forces will be forces of attraction. So if we look at object A, in which direction will it experience a force? To the left or to the right? I'm standing here on object A, and what will I experience? I'll experience a force of attraction. B will attract me. So this is the force of charge B on charge A. And if I go and stand on B, what will I experience?
Force of attraction from
Force of attraction again, yes. So if I'm standing on B, the force of attraction that A has on B is to the left. So this is the force of attraction that A has on B. Okay. The force of attraction that A has on B is opposite in direction to the force of attraction that B has on A. Can you see that? Okay. But they have the same size, or they have the same strength. Okay, now it's important for you to be able to identify the direction of the force that one charge will have on another charge. It's important to know that it's called an electrostatic force, and opposite charges attract, and that these forces will point in opposite directions, but they have the same size. So all those things is important. Somebody's trying to communicate. Let me just see who that is. Oh, my internet is unstable. That's very comforting. Okay, that was Tatenda trying to communicate. She said her phone doesn't want to install Zoom. So electrostatic forces are also called Coulomb forces. So there are two names that we use for forces between charges: electrostatic forces and Coulomb forces. Next, I want us to look at the like charges. So if we have two like charges, we could work with two positive charges or with two negative charges. And I'm going to keep naming them A and B. I know that these forces are forces of repulsion. So these are Coulomb forces of repulsion. Okay, so if I'm standing on A, if I'm standing on A, what will B do to A? It will push it to the left. So the force of B on A is now to the left, where with the opposite charges, it was to the right. It is now to the left. So there you see the force of repulsion is in the opposite direction to the force of attraction. If we go and stand on B, what will A do to B? Repel it, so it pushes it to the right. And you can see on the two diagrams that this purple arrow, the force of A on B is in the opposite direction to what it was when the charges had opposite, when the objects had opposite charges. Somebody else is trying to communicate. Let me see. Okay. It was just Tatenda sharing. Could you please put the slides on the group? Yeah. Later. Okay. What will happen if you go to B that is negatively charged now? What will A do to B? It will push it to the right. So the force of A on B is to the right again, even if the charges change sign from positive to negative. And if I'm standing on A, the force that B will experience, that exert on A, is to the left again. So this is F of B on A. So this is the type of understanding you must have. You must look at the charges, and you must be able to indicate the direction of the force of one charge on the other. Okay. Once again, we can say that the forces are in opposite direction. You can see that this force here, F of B on A, is in the opposite direction to the force of A on B in all the situations. They're in opposite direction, but they will have the same size. I'm busy teaching, Tata. What is it that you want? A what? No. Sorry for the interruption. No problem. Okay, so that's how we identify the forces between charges. Next, I want us to look at conductors and insulators. Now, a conductor is a substance like a metal that can allow charge to flow. The insulators will not allow charge to flow. So conductors will allow electrons and ions to flow freely, where insulators will not, and this computer is very slow in reacting. So examples of conductors would be metals. The human body is a conductor because we have electrolytes. Those are liquids and solutions that can conduct electric current. And examples of insulators would be something like wood or plastic, materials that will not allow charge to flow freely. Next, I want us to look at how the charge is distributed over a conductor or an insulator. sorry, insulators, plastic, rubber, elastic, wood, glass, those are insulators. Okay, so I want us to draw diagrams to show the spread of a charge on conductors and the spread of charge on insulators. So let's go for conductors first. We work, most of the time, we work with round things. Sometimes you can work with something that's got a sharp edge, like a lightning detector. And let's say these are conductors. Now, when you charge these conductors, whether you give them electrons or take electrons away, let's say A will get electrons, there will be millions and millions of electrons making up the charge on the object, and the charge spreads over the object. Because these charges are like charges, they repel one another. So they will go and sit as far apart from one another as possible. There's a force of repulsion that causes the charge to sit. I'm going to use the word sit, as far apart as possible. Now, that is on like a symmetrical object. A lightning detector would not be symmetrical, it's got sharp edges to it. So let's take electrons away from this lightning detector. Then the charge that will be on the object will be a positive charge. And because the electrons leave the object, this positive charge spreads over the conductor in such a way that they will be as far apart as possible. Now, I've only got 3 sharp edges on this object, so I want to show you something. When an object that gets a charge is not symmetrical, where we have points, pointed parts, will have a higher density of charge. And so here at this bottom corner, you'll have a higher density of charge, and at the top corners. And this is how trees work. Trees have points or pointy parts. And there's a high density of charge there. So when we're in a thunderstorm, the lightning is attracted to the points where there's a high density of charge is high places of high voltage. Very interesting. Then I want us to look at the distribution of charge to on insulators. Now, insulator can be a rubber substance like like a balloon. If you, or cone. So if we have a balloon, the charge will not spread over the balloon, evenly over a balloon, because the balloon is an insulator. Charge can't flow on it. So if you rub the balloon on your hair in one place, only that place will be charged. On an insulator, they are only charged where they are rubbed or touched. Okay, are you still with me? Yes, your mic is just off.
Yes, ma'am.
Okay, good. I'm very lonely out here, Talita. It's so lonely, so quiet. I feel like I'm talking to a wall here. Okay,
I'm listening, ma'am.
is everything clear here? You don't have any questions?
No, ma'am.
Okay, good. Now, and this is why this lesson is how to charge objects. In your textbook, it's on page 125 to 127, and I'm going to follow my own way here. So there are three ways of charging objects. You can rub things together, and the friction would cause electrons to be transferred. Or, like in the previous lessons, we looked where object A touches object B, there is contact. So the object, one charged object can touch another object, whether it's neutral or charged, there will be a flow of electrons. And the more difficult one that nobody really wants to talk about is induction. There we go. So these are the three ways in which objects can be charged. Let's discuss them. Okay. Rubbing objects together causes friction, and that leads to a transfer of electrons. And it's very important that whether the object is negatively charged or positively charged, it's only the electrons that will be transferred. Electrons coming onto the object will charge it negatively. Electrons leaving the object will charge it positively. And this is called Primo electric charging. I don't know why, but it is what it is. So let's take a plastic ruler. Now, if the ruler is neutral, it means that for every positive charge, there is a negative charge. So for every proton, there is an electron. And in my sketch, I'm just symbolizing that situation. For every plus, there's a negative, plus negative, plus negative, plus negative. So that's a neutral ruler. If we take a neutral cloth, for every positive, there's a negative. 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 So it's a neutral cotton cloth. Now the magic that happens during rubbing, if they are rubbed together, the friction causes a transfer of electrons. And the transfer of electrons is from the ruler to the cloth. So just to symbolize the cloth. So the electron that is on the ruler, not all the electrons, some of the electrons that is on the ruler will move to the cloth. Let me show you how we symbolize this. Okay, so the friction would cause some of the electrons to move onto the cloth. Now, if you separate these two objects, you take them apart too fast. So what will happen, the electrons won't flow from the cloth back to the ruler in that short period of time. So your ruler will be positively charged. And the cloth will now have extra electrons on it. Okay, are you happy?
Yes, ma'am.
Let me just see if somebody else is wanting to come on here. Hi. Okay, let's go to the next one. If you would just let the ruler lie on the cloth, there'll be no transfer of charge, because a plastic ruler is an insulator and the cotton cloth is also an insulator. So they can lie in contact, they can make contact, but there will be no transfer of charge. There must be friction to transfer the charge. Okay, next one is by contact. When a charged object touches an uncharged object, could be the situation, or even touch another charged object. So here we have A, and it's a negatively charged object. Now, this charge, this transfer of charge during touch means that there's no rubbing. So you need conductors for this situation. If you have an object B that is not charged, it's neutral. If they make contact, the one with most electrons will lose some of its electrons. And in our previous lessons, we discussed the transfer of charge. So some of the electrons will move. And what happens actually is that these electrons, they spread evenly out over the two objects. So when you separate them, that total charge splits in half. But today's lesson is just about the charging of an object by making contact with another object. I'm going to discuss what happens when the object is positively charged. It means that there's an overall spread of positive charges on the object. Now, the only reason for that is that this object has lost the electrons already. So when it touches the neutral object B, who's got the extra electrons? Although it doesn't look like it, B's got more electrons than what A's got. So the flow of electrons will be towards A. Now, there won't be enough electrons moving to A in order to make both A and B negative. So the overall charge spreads positively over A and B. So if a positive object makes contact with a neutral object, the total charge is positive. So both of the objects will be positively charged. If a negative charge makes contact with a neutral object, the total charge is negative. Okay, that's discussing charging an object by making contact with another object, and you need conductors in this case. Next is charging by induction. Now, induction is a difficult word. It comes from induce. You induce change without touching anything in a kind of a way. So induction means to influence the charge without making contact with the original charge. Now, this is a difficult thing. How can that happen? So, what we do to charge by induction, you have your neutral object, which must be a conductor, and you have a charged object, let's say object A has a charge of a negative nature, so it's got an excess of electrons on it. What will those electrons do to any electrons that are in object B? Can you tell me? What will one lot of electrons do to the electrons on another or in another object? There will be a force of, what did you say? Negative will repel negative, am I right? So in B, we have electrons, but for every electron, there is a proton. So B is neutral. For every electron, there's a proton. So B is neutral. That's the meaning of neutral. Now, if you bring this charged object A close to B, what happens is that those negatives that are distributed there, they will be repelled to the bottom. The electrons will go, not the protons. The electrons will go to the bottom. Let me just fix that sketch again. So the electrons, the red ones, they move down to the bottom of object B. So this is what we call polarization. When those electrons are pushed away from A to the bottom of B. This is called a shift of electrons. Because of that force of repulsion that A has on it. And this shift of electrons to the bottom doesn't give B a charge. It remains neutral because for every positive there's a negative. But it is called polarization. So polarization of B has taken place. Are you still with me?
Yes.
Okay. Now, to charge by induction, if you take your finger and you touch B, there, oh, very ugly finger here. Because there, where the electrons has been pushed away, there's a shortage of electrons there. But at the bottom, there's an excess of electrons. So these electrons will flow through your finger. Your body, the human body is a conductor. Electrons, they will leave B. So A hasn't touched B, but if you touch B with your finger, the electrons that were pushed down to the bottom will flow out of B through your body to the earth, out of B. Now, if you take your finger and A away, if you remove your finger, and object A, then there's no flow, no possible flow of the charge back onto B. So B becomes positively charged. That is the final charge on B when you take your finger away, because the electrons left B. So by induction, the charge on the object will be opposite to the charge on the inducing object. The charged object is what we call the inducing object. I just need to read my sentence number 1 here because I think I've changed some words. It will not make sense now. So holding a charged object close to a neutral object and touching the object with your fingers allows electrons to flow in such a direction that the object, the neutral object, will get a charge opposite to the charge on the charged object. That's it. Now it's fixed. Okay, any questions, Talita? Because this is a rather tricky situation. If I use a positive object, A, and I bring it next to a neutral object, then the electrons will be pulled to the top of the object. So you'll have more electrons at the top and the bottom of BB will be polarized positively. So if you touch it with your finger, the object will take electrons in. And then that would result in, if you take it away, E being charged negatively. E will have an overall negative electron. So you see, by induction, you can charge an object, a second object, with an opposite charge to the original charge on the first object. I don't hear you, so I don't know if I'm still in contact with you.
Yeah.
Okay, is this clear or Do I need to talk a bit more? So that is all that I wanted to talk about in this lesson. So now I'm open for any question you have. Doesn't matter which topic.
I think I'm fine.
Are you fine? Okay, that's wonderful news. That you're fine is wonderful news. So I'm going to stop recording.